just going to show you the demonstration I wanted to show you at the beginning of, during the previous hour. So you have to go back to gravity waves, just for 1 second. And so here, the only thing I'm doing is I'm just plotting the interface. So remember, the interface is just a constant times a cosine of k times x minus ct. So it's just a traveling sinusoidal. But what we know is that for gravity waves, the velocity, so the wave speed, depends on the wavelength. So the only thing which I do here is I take 3 different wave numbers. So I superpose sines with wave numbers. Let me just show you that here. Hold on, do it here. With wave number 1, wave number 3, wave number 5. I compute the corresponding wave speed, okay, corresponding to the wave number, and then I just superpose the total, the shape of the interface. Okay, so you see that here h is equal to 10. So h is somewhat larger than all, h, let's think about h times the wave number is going to be a large number. So the tangent of the wave number times h is going to be, the hyperbolic tangent is going to be almost equal to 1. Hold on, what? Sorry, I got it mixed because it was lambda. So here I have the wave number, so it's 1 over. I'm putting the wave number, not the wavelength. Right. So so here when h is large, I have to take h large for to be in the case where. Let me think that right again. So here I have a low, but my wave numbers are on the order of 1. So yeah, so in that case here I'm in deep water. Okay, h is quite large. So this is the deep water case. Remember that in the deep water case, the wave speed does depend on the wave number. Okay, so here, what you see is that, well, the wave, so the black is essentially the sum of the 3, but when you look closely, I also plot the different components. So green, I have my 3 wavelengths, green, pink, and blue, and you see that if you follow, the larger the wavelength, the larger the wave speed. So the green, which is the component of my total wave, which is black, of the largest wavelength, is the one that travels faster. See, the wave speed of green is faster than blue, and the slowest is actually pink. So if you compare pink and blue, you'll see that blue actually moves slightly faster than pink. Yeah? So that would be a typical case for deep water. Now here, this is not a feature because I'm already putting a sign. So I already have a period, a periodic deformation which just propagates. Okay, so that's why it looks already very wavy, because I really have like I'm just superposing 3 sine waves. But this is what you have in deep water. Now if I'm shrinking h, so let me put h equals to 0.01 for instance. In that case now, I am in shallow water, and in shallow water, the hyperbolic tangent becomes the hyperbolic tangent of x is almost equal to x. So you have a 1 over x times tangent, hyperbolic tangent of x. So your wave speed becomes a constant, completely independent almost on the wavelength. So here, in that case, what you would see is something like this. I should speed up because of course it also affects how fast it moves. So let me just have this go a little bit faster. Right, well, it doesn't go that much faster. I'm doing something wrong here. Okay, it doesn't matter. So what you see here is that all of the different wavelengths move at the same velocity. If you look at which velocity the larger wavelengths move, at which wave speed the pink and the blue, they move at the same velocity, which means that your wave doesn't really change shape. You have just features which are going to move. This is what you have when you have shallow water. So you actually also have that when you have a very flat surface and you have sort of a very thin layer of fluid on top. Then you have shallow water. Then if you see sometimes little disturbances at the surface, they will really conserve their shape, and you'll see like features moving like this. I don't know if you've ever observed that. I'm sure from now on you will. Sometimes it happens on your your windshields when you're driving. You really see a little wave, and you actually see one little feature, one little bump just moving like this. This is only possible if all of the different wavelengths which compose that little bump have the same wave speed. So this is when you have shallow water. So this is what I want to show you here. Okay, so that is just wrapping up our discussion in the first hour. And now what I'm going to do is just briefly sketch the derivation for this, but I'm not going to go into all of the detail. I did all of the details more or less for gravity waves. Now the solution method is very similar here. So once you have this ansatz, you take your ansatz, so this, so let me write it for phi. So phi of x is going to be equal to u1 of x plus a function of z exponential I kx minus ct. And this here, the first thing to do is just this needs to satisfy mass conservation if you want. So that means that the Laplacian of this has to be equal to 0, and when you do this, you'll get to an ODE for the function a1 of z, which is a first order ODE, and essentially you will reach to phi1 of x is equal to u1 of x plus a constant exponential I k of x minus ct times exponential minus k z. Now this is the exact same thing as when we got I think it was a hyperbolic cosine for gravity waves, but that was because we imposed a no penetration boundary condition at the bottom. Here we don't. So that's what we get. And you get something similar for phi2. Just do it. So you plug this into the Laplace equation, and you'll get to what the function a1z has to be. This is the first thing. And then the second thing is we have to satisfy a boundary condition. And the first boundary condition we have to satisfy is the kinematic boundary condition. So then let's look at what happens when we plug this into the kinematic boundary condition. And so when you plug, again, so both the solution for the top layer and for the bottom layer have to satisfy the kinematic boundary condition. So we have to have partial h over partial t plus u1 partial h over partial x equal to v1. Now of course we want to write this in terms of the potential, so let me rewrite that. So it's partial h over partial t plus u1, which is partial phi1 over partial x, and remember this is the boundary condition, so this is not written in the bulk, this is only written at y equals to 0 at the boundary, times partial h partial x equal to partial phi1 partial z, because now I called the vertical direction z. And I'm writing it z because gravity is important there. This is the only reason. So equals to partial phi1 over partial z at y equals to 0. Okay. So I had a very good question in the break regarding the ansatz. So let me just go back to it now. When you write this ansatz here, many of you ask why do you assume K and C to be the same for the top layer and for the bottom layer? Right? You don't have to. You could just start with assuming a K1 and a C1 on the top layer and a K2 and a C2 on the bottom layer. But if you remember what happens for gravity waves, your wave number and your wave speed in the flow are going to be the same as the one which you have at the boundary, right? Essentially, that's normal. And so when you actually try to match your boundary condition, you'll see that the only way you can actually satisfy both the kinematic boundary condition for the top layer and the kinematic boundary condition for the bottom layer, they will have to have the same wave number and the same wave speed. So either you take it into your ansatz, you sort of say, well, I know that this has to be this way, or if you didn't, then by the time you try to impose the kinematic boundary condition, you realize that you have to. Okay? So this is what you have here. So you'll find that for H, just like for the gravity waves, H will have to have the form of an H naught times an exponential I kx minus ct. Right? This is what's going to come out of this analysis. This term here, you have to take the dominant term. And we're going to have to take the dominant term of that. And so the dominant term of partial phi1 over partial x is going to be just, remember that phi1 here is u1x plus a small perturbation. Okay? So this here is going to be small, right? Because h is small, every h and the perturbations are small. So this term is small here. And when we looked at gravity waves, where there was no u1x, then we said this is going to be small and this is going to be small. So small times small is small squared, so this is really small. But in that case, this is not, we cannot neglect this term here, because partial phi1 over partial x is not small because of that term here, right? So here we do have to take into account the u1, right? So this partial phi over partial x is going to be a u1 times partial h over partial x, and so this is not small, the u1 is not small, but the partial h over partial x is small, so we have one small. So then we do have one term in this product here which is just small to the power 1. So we do have to take that one into account. And this term here is small. Right? Now if you remember our form now for our disturbance, which is an a1 times exponential I k x minus ct exponential minus k z, right? You see that for this partial h over partial x, right, this partial h over partial x, we're going to have an ik which is going to come out. Now when you differentiate this function here, when you differentiate this function here with respect to x, you get essentially the same function times ik. And when you differentiate this part here, you're going to have a minus k that comes out. Okay, so this PDE is going to look like an algebraic equation, and this algebraic equation, this term here will be a u1 minus the ik, so minus ik times h naught. Okay. This term here, you're going to have a which term is that? Minus k a1. I have to, yeah, minus k. Minus k a1, and this term here, right, when you differentiate h with respect to t, you see that h will have this form here, so you'll have a minus ic coming out. So this term will give you a minus I C K times H naught. So this PDE becomes this algebraic equation. Just plug the ansatz in and you'll get to that. So this is the first kinematic boundary condition, or the kinematic boundary condition for the layer 1, and of course you have the same for the layer 2. So you have something like that. H naught equals to minus U2 IK H naught minus K A2. And actually for A2 it will be a plus, because you'll have a plus here for phi2. Just do the math, you should get to that. Okay, so when you impose the kinematic boundary condition, you get your first two algebraic equation which link, again you should see here, you have an equation which links C and K, which is what you want. Like you want to link the wave number to the wave speed to the wave number. So you impose your two kinematic boundary condition, and then the last one you have to do is to impose, you need to satisfy the normal stress boundary condition. And this is the one which is a little bit harder and longer and more painful to derive. You have to first go, you're linking the jumping pressure to the surface tension times the curvature. Right? So the curvature is going to be a second derivative of h with respect to x. And so if you look at the functional form here, h is going to look like this. Right? So the term in front with the surface tension will have a second derivative, so you expect a minus k squared with the surface tension term. Right? From that. And then you have the jump in pressure, and how do you get to the pressure? You have to get to it from the Ansaldi-Bernoulli equation. So you have to plug in your ansatz into the Ansaldi-Bernoulli equation to get to the pressure, express the pressure at y equals 0, and then you get your third algebraic equation. Okay? So try to do it. It's very similar to what we did for gravity wave, except that it's a bit more, it's a bit more intricate. I think at that stage you may want to actually just plug that into like a symbolic solver or something like that. So when you do that, you get this algebraic equation, I Kc times A1 rho 1 minus A2 rho 2. Right now, don't be surprised if all of a sudden the rho's come in, because the density is in the Ansaldi-Bernoulli equation. Right? You have densities coming into the equation because at some point here you impose the Ansaldi-Bernoulli equation. Plus I times minus rho 1 A1 U1 plus rho 2 A2 U2 times K minus rho 1 minus rho 2 times G H naught equals minus gamma H naught K squared. Now I don't expect you to directly see where all of these terms come from, but this is the one we discussed. Right? This here, the one on the right hand side, is the term that represents the surface tension. Right? Where we had the PDE, that was jump in pressure equals to gamma times the second derivative of h, or the curvature. With the answers that we have, this becomes a minus k squared times h naught. So this is that term here. That here is our gamma second derivative of h with respect to x squared. You see that? You don't see that. Some of you say yes, some of you say no. So so just go back. If you plug everything in, you'll see why it becomes that way. But then you yield your last algebraic equation. So now you have those three algebraic equations, and all you want is really to have a relationship which links C and K. So this is the place where this is the very boring place where you just plug in, try to replace, substitute, do all of those tricks that you can, and that you usually make lots of mistakes in. And finally, when you've done all of your algebra, you get a relationship between C and K, and this is the relationship. I'm just going to write it once. So C equals U1 rho 1 plus U2 rho 2. Actually, what you end up having is, once you substitute everything, it might not be obvious, but once you try to do the right substitutions in all of that, you get to a second order polynomial for K that you solve. For C, which you solve for K. Right? So you'll have you can simplify that, those three equations, to one equation, which is a second polynomial in C, second order polynomial. So yeah. And so when you solve that, you'll get C equals to U1 rho 1 U2 rho 2 divided by rho 1 plus rho 2 plus or minus, this is your minus, if you're thinking of a polynomial, remember ax squared plus bx plus c, you have the minus b divided by 2a, this is your minus b divided by 2a, and then you have a plus or minus the square root of the discriminant. So this is what I'm writing here. This is the plus or minus your discriminant. Rho 2 minus rho 1 divided by rho 2 plus rho 1 g divided by k plus k times gamma divided by rho 1 plus rho 2 minus rho 1 rho 2 u1 minus u2 squared divided by rho 1 plus rho 2 squared. Of course, not something I would expect you to learn by heart. But now, hopefully, if I structured my lectures correctly, at this point, you're thinking, aha. And you're thinking, aha, what? Right? What are you looking for in this relationship? You finally get to your relationship between your wave speed and your wavelength, or your wave number, essentially. Yeah? What are you looking at now? Yeah, so I heard it's the same answer, but someone said positive or negative. Who said? What you're looking for? What is positive or negative? Huh? Yes. Right. At this point, just like remember when you're solving a second order polynomial, the sign of your discriminant is going to tell you whether you have imaginary roots or real roots. Right? So this is what you want to look at here. If you have a negative, let me see that here. I don't have this pointer. I do it with that. What you want to look at is the sign of this quantity here. Right? And we didn't have this problem for gravity waves because we had a c squared equal to a constant. So we knew c was always going to be a real number. Now, our dispersion relationship here is more complicated. And so we have the square root of this number here. And now, depending, which is a discriminant. So depending on the sign of this number, you may have imaginary roots or you may not have imaginary roots. Now the thing is, you don't really have to worry about the sign of the constant. If this has an imaginary part, then you will have a plus I times a number and the minus I times the number. So since there is an other I in the front, it will give you, and this is times t, right? Then this will lead to a ct and a minus ct. So you will have both the growth and the decay. So there will be the wavelengths will grow because the solution with the positive constant is in there. Right? So as soon as this discriminant here is negative, then you know that you have that wavelength is going to be unstable, is going to grow. Because when you plug everything back into your solution, you will have an exponential times a positive number times t in front. And remember that this is dramatic. An exponential times a positive number t is something which blows up really quickly, and there's nothing you can do. The amplitude is going to become enormous, and of course what's going to happen is that your amplitude is going to grow. It's not going to go to infinity, because we are currently assuming that the deformation is small. Right? So as soon as the deformation is no longer small, then you have nonlinearities that kick in, and so our solution method is no longer valid. But what you know is that that particular wavelength is going to grow to a point where you would have to solve stuff and take into account the nonlinearities. But this is the wavelength you're going to see. That one is definitely going to grow. So the whole thing is to notice that when this here, let me call that delta. So when delta is positive, right, then you can say that the perturbation is going to decay. The perturbation is not going to grow. The perturbations do not grow. So that means that our equilibrium solution is stable. But when this number is negative, then the perturbations will grow. And then that means that things are unstable. And our equilibrium solution is never, regardless of what you do. So it's, when something is unstable, I don't know if you remember when you were a kid, you were trying to tilt the plate, and you were like, maybe I could go, you always feel like at some point, there's a point where it starts to become unstable and it just drops, right? But physics is always going to win. The perturbation is always going to win. Eventually, it will always become unstable, right? So there is no chance of the instability not to occur. When you know that the system is unstable, it may take a little longer, it may take a certain time to develop, but eventually there will be a perturbation, and that perturbation will grow. Right? So this analysis here allows you to look at which wavelengths will grow. Okay, so here is our stability criterion then. So let me rewrite that. So this is going to be, everything becomes unstable. So the solution is unstable. When delta is negative, so when you write that, that means that this here is negative, so I'm just going to move this term here to the right hand side. So that means rho 1, rho 2 minus rho 1 times G divided by K. And I'm going to take this rho 1 plus rho 2 and put it in here, plus K times gamma is going to be less than rho 1, rho 2, U1 minus U2 divided by rho 1 plus rho 2. Right? This is our stability criterion. Okay, and so with that, this is valid for all of the different instabilities that we discussed before. So we'll first discuss the Rayleigh-Taylor instability, and then we'll discuss the Kelvin-Helmholtz instability. So here I need to copy that because I'm going to need it later on. So let me just do this. Control C. Yeah. Okay. Okay, so let's start with the Rayleigh-Taylor instability. I think this is 5. So the Rayleigh-Taylor instability is the following. You have your superposed flow. Now again, I'm forgetting whether rho 1 is on top. Well, we'll see it now because we'll see it in the equation. So rho 1 on top, rho 2 on the bottom, and we're assuming u1 is equal to 0, u2 is equal to 0. So of course, yeah, if rho 2 is larger than rho 1, then there is nothing physically that will destabilize. So in principle, what we should see is that it's unstable if, we have an unstable certification, meaning that rho 1 is larger than rho 2. So here, a Rayleigh-Taylor instability if, in principle, rho 1 is larger than rho 2. That's what we expect. Unstable if rho 1 larger than rho 2. This is physically what we expect. Now let's see what our stability criterion gives us. So here we're assuming that u1 minus u2 is equal to 0. And so our stability criterion becomes rho 2 minus rho 1 j divided by k plus k gamma should be negative. Okay. That is the stability criterion for a Rayleigh-Taylor instability. Now let's first assume that there is no surface tension. Okay. If there is no surface tension, right, when is this quantity here? Sorry, I'm blocking it on my screen, but this doesn't help. So if you assume that this term here is equal to 0, right, you note that the system is only going to be unstable if rho 2 minus rho 1 is negative. That means if rho 2 is smaller than rho 1. Right? So this is essentially the physical instability criterion which you have. So you see, if rho 1 if rho 2 is smaller than rho 1, if rho 2 is larger than rho 1, then this number here is positive, right? And so you can never be unstable because this is never satisfied. Now note also that you always want to check the signs of this thing with the terms which are the easiest to get physically. So we discussed surface tension is always going to stabilize your interface, right? And so you note here that what surface tension does is that it makes it harder to destabilize. Note that if you have no surface tension, right, then regardless of the value of k, rho 1 minus rho 2 minus rho 1 g divided by k is always going to be negative. So that means that all wavelengths are going to be unstable. You see that? Yes? So if gamma is equal to 0, so if you have no surface tension, then your stability criterion is, or your instability criterion is the following. This is satisfied for any value of k. So all wavelengths are going to be unstable, right? But what surface tension does is that it does limit the wavelengths which are unstable, or in another way, it makes it harder. It makes it harder for this term here to make the whole criterion work. You see that? It adds a little positive. Vibe here. Right? This term is going to be positive, so this term is going to be a bit more negative to make everything unstable. Now that also tells you that when you have surface tension, right? When you have surface tension, then certain wavelengths are not going to be unstable. Which wavelengths are not unstable? The small one or the large one? If you look here, and if you don't know the answer, then just think of a simple experiment. Right? The small wavelengths are not going to be unstable. Right? And you know that because there are certain cases, there's a simple experiment which you did as a kid, where you had an unstable certification, but where you did not trigger instability. And that is when you plug in the straw in your glass of water and you put your finger at the end and you just lift it up. Right? It couldn't flow. It was not unstable. And that was because of surface tension. Right? What the straw does is that it limits the size of the wavelength. You cannot have a large wavelength because the straw is small. Right? And therefore you don't see the instability because your system doesn't allow for those wavelengths. You have a boundary condition there that just limits the size of the wavelength that you can have in your system. Right? So the small wavelengths, or the large wave number, the small wavelengths are going to be stable, but the large wavelengths, they're always going to be unstable. Okay? That's what you have for Rayleigh-Taylor instability. So this is why you want to do all of this analysis, because from those simple dispersion relations, you get a lot of information out. Okay, this is Rayleigh-Taylor instability. Now let's move to 9 minutes for the Kelvin-Helmholtz instability. So let's go to 6. Kelvin-Helmholtz instability. Here we're not assuming any term to be small, so they're all big. So we're not assuming U1 to be 0. So the Kelvin-Helmholtz stability is the following. So now we have this shear flow, U1, U2, rho 1, rho 2. And here we're going to have a competition between two things. We have a stabilizing effect and we have a destabilizing effect. The stabilizing effect comes from the stable stratification. This is what you have, if you're looking at the waves which are triggered by the wind blowing on top of the ocean, or the example we saw in the movies where we saw those clouds going a bit crazy. What stabilizes the system is the stratification. You have a heavier fluid on the bottom and a lighter fluid on top. So here we're assuming that the stratification is stable. So rho 1 is smaller than rho 2. So in principle, if there was no shear flow, we'll just have gravity waves, but nothing is going to blow up. We're not going to have anything which is dramatically unstable. But when you add shear, so now let's assume that U1 minus U2 is not equal to 0. Right? This is the stratification stabilizes, the shear destabilizes. Right, and so here our instability criterion is the following. So we have that here, we write it again. So rho 2 minus rho 1. So rho 1 G divided by K plus K gamma is equal to 4 rho 1 rho 2 U squared. And here I could be making mistakes when I'm copying, because I'm copying quickly. So that's, sorry, this is our this is our instability criterion. So let me just plug this number here. Let's plug this as a function of the wavelength. Right, so here I have K, and I'm going to plot the function f is equal to rho 2 minus rho 1. This is a function of K, it's a function of the wave number, plus K gamma. So note here that the number rho 2 minus rho 1 is a positive number. Okay, so that term here looks like a 1 over K, a 1 over X. So when k is small, I have something like this, like a hyperbole. Yeah? This here is because of the 1 over k. This is when k is small. And then when k is big, this term here is small, right? And that term here looks like a linear function. Right? So far away, I'm going to have this. So that is my function. That's my function f as a function of k. It looks like this. Okay? And so what you have here is that if you think about the value of u squared, right? When are you going to be unstable? You're going to be unstable when, so for different values, if u is real, so let's say u is equal to 0. When u is equal to 0, we are stable. Right? When u is equal to 0, you have nothing which destabilizes. So all of this region here is the region of stability. If you're thinking about here constant, just thinking about the value of 4 rho 1 rho 2 u squared divided by rho 1 plus rho 2 as you increase u. When u is equal to 0, you're here, you're always below the curve, so you're always stable. Right? Every single wavelength is stable. Now, you see that there is a critical value for u. Right? There will be a critical value for u at which one wavelength, this wavelength here, is going to become unstable. You see that? That's going to be the wavelengths you're going to see grow in the Kelvin-Helmholtz instability. Right? But you need a critical value for u. If there is surface tension, you need a critical value for u to see the instability. And now, if you go to larger value of u, you see here, right? All of the wavelengths which are in this region here, between that point and that point, will be unstable because they're above the curve. All of the values of the wavelengths here and here are going to remain stable. So this is a stability diagram. Here you have stability, see, and here you are unstable. Right? So note, the important part is really the very small wavelength. So the very small wave number, which corresponds to very large wavelengths, are stable. So you have a minimal size of a wavelength that you're going to see, which are going to be unstable, right? And you have and you see also at surface tension. So this part of the curve here, right, is the part where you have surface tension. You see that surface tension stabilizes the very, very large wave numbers. That means it stabilizes the very, very small wavelength, which makes sense. Right? Surface tension is essentially going to prevent seeing this instability being triggered for very small wavelength. Yeah. Do you see that? So for the say that again. So here, so I'm just trying to represent when are you going to be stable, when are you going to be unstable, right? So just think about if you have control over u2 minus u1, so you're slowly increasing the velocity, right? So you start with a case where you have no shear, right? Then u is equal to 0, right? So if you look at this graph, when u is equal to 0, right? This function here is essentially that function f of k here is always positive, it's strictly positive. So that means that here you're always below this number here. So you're never unstable. This is never satisfied. Okay, let me just rephrase that. Maybe this is, you could also write that as you just put this on that side, and when is the difference negative? I'm not sure I got the question actually. What was your question? But are you able to, because I was going to say So you need to be able to, in those problems of instability, you need to be able to explain what are the governing equations. I don't expect you to know how to come up with the ansatz and know the derivation, but then understanding a stability diagram, this then I expect you to be able to do. So once you have the dispersion relationship, to be able to say, well, this is the wavelength which is going to grow or not grow, this I expect you to do. So this is why I think I got the question that you actually didn't understand now. Am I right? So then I'm going to try to re-explain. This is your stability criterion. When this relationship here is satisfied, you are unstable. What you want to know is like for which case, for which wavelength are going to be unstable. What is the wavelength? What is the size of the unstable feature I'm going to see when my system destabilizes? Remember the image of the Kelvin-Helmholtz instability. It was a very periodic feature. It was not just, you have nothing and then you have just random stuff happening with all kind of wavelengths. There was a very clear wavelength which destabilized. Do you remember that video? Okay, so go to YouTube and type Kelvin-Helmholtz. I'm reaching the end of the hour. But there's a clear wavelength which destabilizes. That's what you want to know. What are the wavelengths which are unstable? Because those are the ones you're going to see. Those that are stable, they're not going to destabilize. You're not going to see that wavelength. You're not going to see the interface deform. Yeah? So you have to look for which case here, for which case do I satisfy this relationship. So what I'm doing here is I'm plotting this function as a function of k. And that looks like this. Right? Yes? If this number here is below that curve, then I'm stable, because then I don't satisfy this relationship. If this number here is above that curve, then I am unstable, because I do satisfy the relationship. Is that clear? Yeah. So when u is really small, when u is 0, right? U is 0 is here. Right? U is 0 is here. It's always below the curve. So when u is small, all the wavelengths are stable. Right? There is not a single wavelength which is going to be such that that number here is larger than this. Okay? Now if you think about slowly increasing u, there is one u at which one point, you see, for all of these wavelengths here, I'm going to be below. If I take u such that 4 rho 1 rho 2 times u squared is here, you see here for all of this range of wavelengths. So those are short wavelengths. That means those are short wave numbers. Sorry. So those are long wavelengths. For these long wavelengths here, I'm stable. So I'm not going to see an enormous wavelength become unstable because they are stable. You see that? But then for this range here of wavelength, of wave number, I am going to be unstable. So those wavelengths here, this is what I see. Those are the wavelengths. I mean, here I'm plotting everything in terms of wave numbers because it's easier to plot the function, but it corresponds to wavelengths. Those wavelengths are the ones you're going to see destabilize. That's why you see this very regular pattern appear. Yeah? And then, my last point is essentially, you see from this diagram, you see that the small wave numbers, so the large wavelengths are always stable. Right? Here, regardless of u, the very, very small wave numbers, they're always underneath the curve, so they're always going to be stable. And there's always going to be one wavelength here. At some point, you become unstable. And then on that side of the curve, this side of the curve, by the way, you wouldn't have if you neglected surface tension. If you neglected surface tension, then you just have a hyperbole. But this little part here tells you that the surface tension, what it does is that it restabilizes the very, very large wave numbers. So the very, very small wavelength features don't become unstable because of surface tension. Yeah? Is that good? Okay. So I'll see you on Friday.